So in this video we are going to discuss Bezout's identity, also called Bezout's lemma, which is a useful little fact in number theory. So it's all about greatest common divisors in the Euclidean algorithm, so please be familiar with the concept of greatest common divisor and the Euclidean algorithm method for finding greatest common divisors before watching this video. If you're not familiar with those, I have a video in the playlist on number theory entitled the Euclidean algorithm which goes through all of that. So watch that first. So what does Bezout's identity say then? It says that if you have two integers, m and n, and we have their greatest common divisor, which we'll call d, so d is equal to the greatest common divisor of m and n, then Bezout's identity says that there exists integers, so there exists integers which we'll call z1 and z2, such that this equation is true. z1 times m plus z2 times n is equal to d. So what this is really saying is that it's possible to find some integer multiple of m such that if you add it to some other specially chosen integer multiple of n, that it gives you d. That there exists an integer multiple of m and an integer multiple of n such that if you add the two together, it gives you this value d that is the greatest common divisor of the two. That z1 and z2 exist that satisfy this equation. So the proof of this is important, the fact that we can do this. This is an important result for many future proofs in number theory. The proof of this itself comes very naturally from the Euclidean algorithm, and I want to demonstrate that initially by means of an example. So we'll take the example that we actually used in the video on the Euclidean algorithm. So we'll take 36 and 20. So m is 36 and n is 20. Let's find the greatest common divisor of these two with the Euclidean algorithm. So we write 36 as some quotient times 20 plus some remainder. So it's 1 times 20 plus 16, where the remainder is positive and less than 20. Then remember, the great way the Euclidean algorithm works is that we conclude from this that the greatest common divisor of 36 and 20 is the same as the greatest common divisor of 20 and 16, and we go through the proof of why that is true in the video on the Euclidean algorithm. Then it might not be immediately obvious what the greatest common divisor of 20 and 16 is to us, so we apply the same trick. So we say write 20 as some quotient times 16 with remainder. So we'll get that it's 1 times 16 plus remainder 4, which is of course smaller than 16, positive and smaller than 16. And now we can conclude that this is equal to the GCD of 16 and 4, and now 16 is equal to an exact integer multiple of 4, and therefore you can conclude that the GCD must be 4, because 4 is certainly going to divide 16, and 4 divides 4, and it's the biggest integer that divides 4. No higher integer is going to divide 4, so there cannot be a bigger common divisor than 4, so you've got your greatest common divisor. So how can we now use this to see that it's going to be possible to write Bezout's identity for 36 and 20, so when m is now 36, n is 20, and d is 4, how can we see that there's going to be a z1 and z2? Well, we can actually find what they're going to be equal to. You see, we can use this equation here that is second up from the bottom in the Euclidean algorithm, because this has got our GCD here, and then it's written not quite in terms of m and n, it's actually written in terms of n here. This is 20, and then we've got the first remainder from the first line of the Euclidean algorithm. But look, we could rewrite this to get 16 is equal to 36 minus 1 times 20. So I could rewrite this as 16 is equal to 36, and then we could have plus minus 1 times 20. And if I substitute that in here, then now I'll have an equation involving just my m and my n and my common divisor. So doing that, we get that 20 is equal to, and then we've got 1 times 16 plus minus 1 times 20 plus 4. simplifying this, we've got 20 is equal to 36 plus minus 1 times 20 plus 4. And then just taking things onto the other side, we've got minus 1 times 36 plus 2 times 20 is equal to 4, which is exactly what we wanted. I put the brackets in slightly strange positions. It would probably look better if I'd written it consistently. So I put the brackets around the coefficients rather than the number in the second case. Ugh, and I've done the same thing again. Let me rub that out. So this looks slightly better, hopefully. So this, if you like, is Z1 here, minus 1. Here is Z2, which is 2. I found integer multiples of the 2 such that when you add them together it gives 4, and clearly this equation is true. This is 40 minus 36 does indeed give 4. So here is how Bezout's identity is true for 36 and 20, and we've actually managed to find Z1 and Z2. And this works actually in the more abstract context as well. Sorry, not abstract, more general context. It works for all m and n's. I'm going to try and explain that to you now. So now let's take our general m and let's take our general n, those are integers. And now for some cases it is trivial finding the greatest common divisor, and the fact that Bezout's identity is true is also going to be trivial. So one of those cases is where the modulus of these two numbers m and n are equal to one another, so they might actually be the same number, or one might be the negative of the other. In that case, the greatest common divisor is just going to equal this modulus, so d is going to equal that value, whatever it may be. And the fact that Bezout's identity is true in this case is trivial because you can just set, for instance, z1 to 0 and get rid of this bit, and then just either make this 1 or negative 1 as is necessary to make this true, because mod n is equal to d. If n is a positive number, that means that n is just equal to d, so you'll just need a positive 1 there. If n is a negative number, then that means that minus it is equal to d, so you'll just need a minus number there to cancel with the negative here to overall make the positive version of it. So Bezout's identity is trivially true in this case, as indeed finding the GCD in that case was trivially true. So we might therefore assume that the moduli are not equal to one another, and without loss of generality we'll say that the modulus of m is less than the modulus of n. Now we will proceed with the Euclidean algorithm in this non-trivial case now, and we will write m as some quotient q1 times n plus some remainder r1, where r1 is guaranteed to be non-negative and less than the modulus of n in size. Now, it might be the case that r1 is equal to 0. This is also a pretty trivial case. In that case, m is a direct multiple of n, and in that case, the GCD of the two is the modulus of n, not just n because n might be a negative number, but the modulus of n. And in that case also, the fact that Bezout's identity is true is pretty trivial because in that case again, d is going to equal the modulus of n. So again, you can do the same trick. You can just put z1 is equal to 0, get rid of this bit, and then just make z2 what is necessary, either plus 1 or negative 1. Again, it will depend on whether n is a positive or negative number. If it's a positive number, then plus 1. If it's a negative number, then put minus 1 there. So now let's go to the less trivial case. Let's get rid of that is equal to. It's going to be strictly greater than now. In this case, what we use the key principle that underlies the Euclidean algorithm to say that the GCD of m and n is equal to the GCD of n and r, and we now proceed to try and find the GCD of n and r. Now, the process obviously continues on. It might only need one more line because n might be a direct multiple of r, so we write n is equal to q2 times r, and by the way it's called r1, so I'll subscript it 1. So we write n is equal to q2 times r1 plus r2 using Euclidean division, and if R2 is equal to 0, then we're done because n is a direct multiple of R1, therefore R1 is going to be the GCD because it's a positive number. Remember, we've chosen positive remainders using Euclidean division here. If not, then we'll apply the same trick again to say that now what we're after is the GCD of R1 and R2, and we'll then write R1 as a quotient, which will be Q3 times R2 plus potentially an R3, and we'll continue going on until the remainder that you get here is nothing. So at some point we'll get down to potentially R, we might have to go on n times, let's say, and we'll get to R n minus 1 is equal to, it'll be Q n plus 1 times Rn overall. This might be our final equation in the Euclidean algorithm. And then we conclude that Rn here is our GCD. The reason that Bezout's identity is going to hold true is exactly the same as what we did here. We can use all of the lines from the Euclidean algorithm to get the Bezout's identity coefficients. Now, if we go back to the concrete example up here, remember the line that was actually of great use to us was the second from bottom line rather than the bottom line, because the second from bottom line has the GCD appearing here, and then it has two other bits, a quotient times something and is equal to something else over here. Now, in this simple case, this thing over here was already n. In the more general case, that's not going to be n. It will be some other remainder. But these two things we can then replace with things from lines higher up, and then we can work up and up to eventually substitute in, hopefully, things in terms of our original m and n. So going back down to here, we need the second to bottom line to appear here. So let me add it in. So the second to bottom line is going to be Rn minus 2 is equal to, and then it will be Qn times Rn minus 1 plus Rn. And here then is our GCD, so I might actually replace that with D. So rewriting this line out, we've got Rn minus 2 is equal to Qn Rn minus 1 plus D. And now we want to get rid, this is fine, this is just some integer, that's absolutely fine, but these things, we want to get rid of them. We want actually somehow to get m and n back in here. And what we're actually going to need to do is do loads of substitutions, back substitutions using these lines from higher up here. So it actually, I think, is clearer to start right from the top. So if we go right to the top up here, we have our first equation, which is that m is equal to q1n plus r1. We can rewrite this as R1 is equal to m minus Q1 times n. We can then substitute that into the next line down. Here we've got n is equal to Q2 R1 plus R2. Rewrite this as R2 is equal to n minus Q2 R1, because that's then going to be substituted into the next one down. It's going to come in here. But we firstly need to get rid of the R1 and write it in terms of m and n. So R2 can be written as n minus Q2 times m minus Q1n. Multiplying out that bracket, we get n minus Q2m. And this gets very complicated, and we're not going to do the whole thing, but you will see the idea of what's happening here. So then gathering the like terms, so we'll end up with 1 minus Q1 Q2 times n minus Q2 times n. So you see, this is clearly an integer because all the Q's, remember, are always integers. So multiplying two of them together will give another integer. Doing the negative will give another integer, and then adding it to 1 will give an integer. So these coefficients are still going to be integers. So we've written R2 then as a combination of integer multiples, a linear combination if you like, where the coefficients are integers of n and m. And we can proceed on, so this third line, what we can do is write this as R3. So here's the third line, remember? R3 is equal to R1 minus Q3 R2. And then we can substitute in for what R1 is in terms of M and N, which is here, and what R2 is in terms of M and N. And overall then just collect the terms together. And I might do this one final time just to demonstrate this. So R3 is going to be equal to M minus Q1N. So I've just substituted that in for R1. And it's going to be minus Q3 times what we've got here for R2, which is 1 minus Q1 Q2 times N minus Q2 times N. So simplifying this, we've got M minus Q1N, multiplying out that bracket, we've got minus Q3 plus Q1 Q2 Q3, and I'll put that all in a bracket, which is getting confusing, so put that like that, times N. And then we've got minus times minus, so plus Q2 Q3 times N. And then we can collect like terms together. So we'll get 1 plus Q2 Q3 times N plus, and then we've got Q1 Q2 Q3 minus Q1 minus Q3 times N. But the point is, I might have made mistakes here. I apologize if I have. Your algebra might be better. But these things, whatever they are, they're integers, because all of these Q's are going to be integers. So we're just adding and multiplying and subtracting. All of that remains in the integers. The integers are closed under all of those operations. So you've still got an integer multiple of m plus an integer multiple of n here. And then you proceed down the rows in this way until eventually you'll get to this one. And then if you continue on like this, you'll have, by this point, formulas for Rn minus 1 and Rn minus 2 like this, where you've got an integer multiple of m and an integer multiple of n. You can just substitute those in, and then you'll be able to get that d is this one minus this one. And simplifying that all together, you'll get an integer multiple of m plus an integer multiple of n. So the Euclidean algorithm then is where Bézout's identity comes from. And whilst you're doing the Euclidean algorithm, by the way, you could be writing down these corresponding equations next to it. So I might do an example of this, actually. We'll go over here and do one final example. So let's take the example of, I'll just make up some numbers, 24 and 56. That might be a very bad example. No, it's not. I thought for a moment that it was a direct multiple of 24. It's not. Good. So let's do this. So 56 is the bigger one, so we write it as 24 times some quotient. We're going to use 2. So 2 times 24 is 48, and then the remainder is going to be 8. What you can do, meanwhile, and this, sorry, I have picked numbers that makes this a very easy example, but never mind. What you can do alongside is now write that remainder as this integer multiple of m and the plus an integer multiple of n. So 8 is going to equal 1 times 56 plus negative 2 times 24. So you can keep track of these equations as you go through the Euclidean algorithm. And if you do this, it's actually called the extended Euclidean algorithm, to find not just the greatest common divisor, but also the coefficients of Bézout's identity. Carrying on, you then say the problem is reduced to the GCD of 24 and 8. That's pretty boring, because now 24 is equal to 3 times 8. So it's a direct multiple of 8. So we've got our answer. GCD is equal to 8, and in fact this is therefore Bézout's identity. Let's do another example, because that one was too easy. Again, making up numbers. Let's do 75 and 44. Let's see what this yields. So first line of the Euclidean algorithm then. 75 is equal to 1 times 44 plus what's its remainder going to be? So if we add 30 to 44, we get 74, so 31. So plus 31. Rearranging that to do the extended Euclidean algorithm, we get that 31 is equal to 1 times 75 plus minus 1 times 44. Now, second line of Euclidean algorithm, we will write 44 is equal to 1 times 31, and then it's going to have remainder 13. Rearranging that, we're then going to get 13 is equal to 1 times 44 plus minus 1 times 31. Now we don't want 31, so we're going to actually substitute in this first line in. So we're going to get 13 is equal to 1 times 44 minus, and it's going to be 1 times 75, so I'll just write that as 75 for now, minus 44. And now collecting that together, we're going to get minus makes a plus, so we're going to have 2 times 44 plus minus 1 times 75. Let's just check that that's correct. So 2 times 44 is 88, minus 75 will give us indeed 13, so that's lovely. There we go, that's the second line of the extended Euclidean algorithm done. Now let's do the third line. 31 is equal to, and I think 2 times 13 goes into that. That will make 26, and then we'll get remainder 5. Doing the third line of the extended Euclidean algorithm, therefore gives us 5 is equal to 1 times 31 plus, plus minus 2 times 13. Now, of course, we don't want either 31 or 13, so we need to substitute this expression and this expression in so that we get it instead in terms of 75 and 44. So we'll get 5 is equal to 1 times the expression for 31, which is 75 minus 44, and then plus minus 2 times the expression for 13, which is 2 times 44 plus minus 1 times 75. So this is a much better example, much more non-trivial. So let's collect things up. Minus 2 times 2 is going to give minus 4, lots of 44. Minus another one is going to give us minus 5. So minus 5 times 44. And then 75, we've got 1 here. And then we've got minus 1, minus 2 gives us overall 2. So that's going to give us plus 3 times 75. And I feel like I should just check that that is actually true. Let's do this. So 3 times 75, what's that equal to? That's equal to 225. 5 times 44 is 220. Not 222, it's 220. So minus 220. So yes, it works. Minus 220 plus 225 is indeed 5. Excellent. So it's going well. Let's continue on. Fourth line of the Euclidean algorithm is then that 13 is equal to 2 times 5 plus 3. So I'm getting the impression that the GCD of these two numbers is going to be 1. They're going to be co-prime to one another. But let's continue on anyway. So we've got 13 is equal to 2 times 5 plus 3. Doing the fourth line then of the extended Euclidean algorithm is that 3 is equal to 1 times 13 plus minus 2 times 5. So again, we don't want 13 and we don't want 5, so we use our previous equations. So we've got this one and this one. Doing this, we get that 3 is equal to 1 times 13. So 1, in fact, we might just get rid of that 1. It's equal to the 13, which is 2 times 44 plus minus 1 times 75 plus minus 2 times our 5 one, which is minus 5 times 44 plus 3 times 75. Let's simplify that. So we're going to get how many 44s? So we've got 2 here, and then we've got 10 here, so 12 times 44. So you can see how this is actually doing quite amazing things. 12 times 44, and then 75, we've got minus 2 times, I think that's 3, not negative 3, yeah, so it's 3, that's fine. So minus 6, minus 1, so we've now got minus 7, plus minus 7 times 75. So checking this is becoming less and less trivial. Am I going to attempt to check that? We should check it. So 440 is 10 times 44. 2 times 44 is then 88. So we've overall got 528 there. Negative 7 times 75. How are we going to do this? 7 times 7 is 490. So we've got minus 490. 7 times 5 is 35, minus 35. So we've got minus 525. Oh, look, it works. Isn't this beautiful? So I'm just going to underline it to remind myself where it actually is. The next line, and I'm going to put some space, so we'll come down here. Next line of the Euclidean algorithm then is that 5 is equal to, damn, we're going to still have 2 lines, I think. 5 is equal to 1 times 3 plus 2. So the next line of the extended Euclidean algorithm is that 2 is equal to 1 times 5 plus minus 1 times 3. And then we again need to put in this one and this one in here. Let's do this. I'm sure you've got the idea of this by now, but I do want to finish this just for pride now, for satisfaction, so we'll do this. So 2 is equal to, let's put in the expression for 5, which is here. So it's going to be minus 5 times 44 plus 3 times 75 plus minus 1 times 3. So that's just going to be negatives for all the ones on 3. So we'll have minus 12 times 44 plus 7 times 75. Collecting those together, we then end up with minus 17 lots of 44 plus 10 lots of 75. So just because I don't want this to go wrong, let's actually check this again. So we've got 750 here. 17 times 44, so 10 times 44 is again 440. 7 times 44. 7 times 4 is 28, so you get 280. 7 and 28 there as well, so all of these need to be minus. So putting them all together, we've got, putting these two together first, we'll have minus 600, minus 720, minus 28 is going to be minus 748. Brilliant. So 750 minus 748 is indeed 2, so that's absolutely working perfectly. And now, hopefully, this is going to be the final line. Yes, it is. So, well, not the final line of the Euclidean algorithm, but the final line of the extended Euclidean algorithm. So 3 is equal to 1 times 2 plus 1. And then the final line is just 2 is equal to 2 times 1. So 1 is the greatest common divisor of the two original numbers, which were 44 and 75. They are co-primed to one another, is the word for when the greatest common divisor is equal to 1. So there is no bigger positive integer that divides both of them. So then the final line of the extended Euclidean algorithm is then this one here, which is that 1 is equal to 3 plus minus 1 times 2. So then we just need to put in this equation for 3 and this equation for 2, and we'll get that 1 is an integer multiple of 44 plus an integer multiple of 75, i.e. Bézout's identity. Doing this, 1 is equal to 12 times, and I'm putting the brackets in the wrong place, or not the wrong place, but the place that I haven't put them previously. 12 times 44 plus minus 7 times 75, that's 3, and then we want the negative version of 2, so we want plus 17 times 44 plus minus 10 times 75. So this gives us 29, I think, 44s, and then we've got minus 17 lots of 75s. So let's do our final little bit of arithmetic just to make sure that this is true. So 29 times 44 then, gosh, I'm trying to decide, do I want to do 30 times 44 and take away 44? I think I will do that. So 30 times 44 is going to equal 3 times 440, which equals 1,200, 120. Taking away 44 whilst we can, we'll get 76, I believe. Let's just check that. 76 plus 44 gives 110, 120. Brilliant. So if we just add 1,276 then, I believe, is the answer to that. And now let's do 17 times 75, or minus 17 times 75. So we'll get minus 750. And then 7 times 75. 7 times 7 is 49, so minus 490. 7 times 5 is 35, so minus 35. So all of these things, I think, added together. So adding 750 to 490 will give us minus 1,100, or in fact 240, minus 35 will give us minus 1,275. Bingo. 1,276 minus 1,275 is indeed equal to 1. So there you go. There is Bézout's identity for 44 and 75, found by the extended Euclidean algorithm. And with that, we will finish the video. Thank you very much.